Hello everyone, let us solve the problem jump game 4. So, given an array of integers ARR, you are initially positioned at the first index of the array. In one step, you can jump from index I to index I plus 1, where I plus 1 is less than the length, I minus 1, where I minus 1 is greater than or equals to the 0th index, or j, where ARR of I is equals to ARR of j and I is not equals to j. Return the minimum number of steps to reach the last index of the array. Notice that you cannot jump outside of the array at any time. That's pretty obvious. Okay, let's see the example. 100 minus 23. Okay, the output is 3. You need 3 jumps from index 0 to 4, 4 to 3, 3 to 9. Okay, how? 100, 0 is 100, index 4 is again 100. We can jump to an index where the value is same as our current index. Okay, so we did that. From 4 we went to 3. We did this one, minus 1. Okay, then from here we went to directly at index 9, that is the last index. We did this step. Okay, so that's how our answer is 3. 1, 2 and 3. Okay, this one is 7. Start index is the last index. All right, no need of taking any step. This one you can jump directly from index 0 to index 7. Yes, index 0 to index last index, right? Directly with one jump. Okay, let's discuss the first example. We are at initially index 0. We have three choices: to go to the left, to go to the right, and to go to an index where the value is same. Okay, so we go to index minus 1, we go to the right index, that is 1, and we go to index 4. Okay, fine. Now index minus 1 is not possible, right? It's out of bounds. Okay, fine. Now let us look at this index. Where can we go? We can go to 0, right? We can go to 2, right? And also 2, right? Because it's the right as well as the value is same, so doesn't matter, this much is fine. Okay, now we already went to index 0. Okay, so let's not go into that. Now let's look at 4. From 4, where can we go? We can go to index 3, we can go to index 5, and we can go to index 0. Fine. Now we already came from 0, right? We don't want to go back, we won't go back, doesn't make any sense, right? Now let's look at this. From index 2, where can we go? We can go to index 1, and we can go to index 3, right? Index 1 and 3. Now since we came from index 1, there is no point in going back to it, right? So let's not go there. Now index 3, this one, where can we go? We can go to index 2, right? Then we can go to index 9, and we can go to index 4 again. That's where we came from, so let's not go there. Similarly, from 5 we can go to index 4, where we came from. Sorry, 4. Let's not go there. Fine. Where can we go? We can go to 6. Where can we go more? We can go to 7 as well, right? Same value. Now the thing is, if you observe, from 3 we made a jump to index 9, right? That is this last index, which means that from here we can take a jump to the last index, and our work would be done right here. Right here, we don't need to explore anymore, right? So what is this? Interestingly, we have built this stuff. Now what is this? This looks like a graph to me, right? Now since it's a graph, we can definitely build an adjacency, right? The 0 we can go to 1, minus 1 we can go to 1, we can go to 4. Similarly, 1 can go to 0, 2, like that we can build an adjacency, right? Okay, now let's create its adjacency. Okay, let's see. From 0, where can we go? We can go to 1, and we can go to 4. Let's not consider the out of bound case. Okay, from 1, where can we go? We can go to 0, we can go to 2, right? From 2, where can we go? We can go to 1, and we can go to 3. Fine. From 3, where can we go? We can go to 2. From 3, we can go to 4, and from 3 we can also go to 9, right? From 4, where can we go? We can go to 3, 5 and 0. From 5, where can we go? We can go to 4, we can go to 6, and we can go to 7 as well. 6, 7, 8 and 9. From 6 where can we go? 5 and 7. 5 and 7 left and right. Right, no other same value. Okay. From 7 we can go 5 and 6. Also we can go to 8. That is the right. From 8 we can go 7 and we can go 9. Right, 3 is not present anymore. Okay, from 9 we can go to the left 8. We can't go to right, out of bounds, and we can go to 3 as well, same value. So this is our adjacency. Right, now one more thing, if you observe, we started from here, right? We started from here. Okay, now after a certain time we reached these positions. Let's call this span 1. Okay, after then, from this level we reached these positions, right? These positions, we took another unit, right, of time or whatever you say. Then from these levels we reached these levels, right? That took another. Now we can clearly see that we are going on a level wise order, right? We are going a level wise order. At each level, after an each level we are reaching certain indices, right? And we are continuing further. Okay, and clearly after this 111, that is after 3 levels, we finally reached our destination, right? That took us 3 levels. Let's call it 3 steps. After 3 steps we reached our destination. That was exactly the case here, right? From 100 to 4 to 3 to 404, index 9. We took 3 steps. Fine. So this clearly indicates that we have to apply BFS, isn't it? We are going level by level. At each level we are reaching certain points, and from all those certain points we are trying to go to their next indices, right? Taking one more level or one more step. Okay, also our question is to find the shortest distance or minimum steps or whatever. That clearly indicates that we have to use BFS, right? And it is applicable. Why? Because it's a graph, isn't it? So our intuition is pretty clear now. We will perform a BFS. We will begin from 0, index 0, and we will go to the all possible places, right? So let's start. Initially number of steps is 0, right? 0. Let's go. From 0 where can we go? We can go to index 1 and we can go to index 4, right? All possible places visited. Okay, so our steps, number of steps becomes 1. Also, since we don't want to visit a place more than once, so for that we will mark the visited places as visited. Okay, so this place has been visited. Let's mark it using a tick mark. From 0 to 1 we visited 1, and from 0 we visited 4. So these 3 places has been visited by costing 1 step. Okay, let's move further. From where can we visit? We can visit 0, but we have visited it, so let's not go there. From 1 we can visit 2. Okay, so let's mark it as visited. Fine. From 1 where else can we go? Nowhere else. Fine. From 4 where can we go? We can go back to 0, but it's visited, so let's not go there. From 4 we can go to its left, that is 3, visited. From 4 we can go to its right, visited. All possible places visited by taking 1 step. Now let's try from here. Which places can we visit from 2? We can visit 1, we can visit index 3, but all of them are visited, right? So this place is useless now. Okay, now let's check 3. From 3 where can we go? We can go to 2. Okay, we can go to 2, but this place is visited. We can go to 4, the right, but that place is also visited. And we can go to 9. We can go to 9. Okay, from 5 where can we visit? We can visit 4, but that place is visited. From 5 where we can visit 6. Okay, 6 can be visited. Where else can we go? We can go nowhere. Okay, so we took one more step to explore these indices. Okay, now since we have discovered them, now let's step on them. Okay, we step at 9, index 9. As soon as we step on 9, we realize that it's the last index. That is where we wanted to visit, actually our destination, isn't it? So we have found our answer. How many steps did we take? We take 1 plus 1 plus 1, that is 3 steps. So 3 is going to be our answer. Now let us quickly look at the code. We initially have our n variable to store the length of the array. In any case, the length is 1. That means that our start position is the last position, right? In that case, we don't need to take any step to return a 0. Otherwise, we create a map of integer, list integer. Now what is that? This integer would be the element, and the list would be the index where we can visit. Index 2 dot dot dot, all the places where we can visit, right? Which is nothing but from 100 we can visit this 100, right? Index 4, right? Or you can say wherever the element is present, we map their indices to that particular element in the map. Okay, now we traverse the array. If that mapping is not present, we put initialize that mapping, right? A new array list, and in that array list, empty array list, we add that index. Okay, now we can make this shorter as well. Like, let me copy it. Compute if absent, error of I, value would be new array list, and in that we want to add that index. Okay, this part is this one. Okay, and this add part is this one, just for simple explanation for now. Okay, now we create our queue, okay, in which we will be storing all these, right? Initially we had this in our queue, then we pulled out from 0. Where can we visit? We can visit 1 and 4, added them to queue, done. Pull this out from 1, where can we visit? We can visit 2, add 2, then pull this out. Then this one from 4, where can we visit? 3 and 5, add them to queue. Its work is done. So that's what the queue is for, right? So also it's a BFS, right? In that, at the 0th position, that is our starting position. Now since we are standing at our starting position, that means it's already visited, right? For that we have created a boolean array and marked the starting position as true, and a variable steps that will count the steps, okay, at each level. Now let's start the BFS. While our queue is not empty, get the size of the queue. Pretty standard approach. Size minus minus greater than 0. Pull out the topmost integer from the queue, or the index. It would be the index. Okay, if in any case that index is the last index, n minus 1, directly return the number of steps, this one, right? Otherwise we have 3 tasks to do: go to left, go to right, and go to indices where value is same. Fine. Now what is left? Let's say L, current minus 1. Now let's check the conditions. If L is inbounds, okay, and L was not visited before, then we visit it. In our queue we add L, and in our visited array we mark the Lth position as true. Let's go to right. R equals to current plus 1. If R is lesser than n, length of the array, that means inbounds, and R was not visited before, add this to the queue and mark R as true. And the third task is go to the indices where the values are same, right? For that we will first see if that value at that particular current index is present in the map or not. Let's say we have 100. Okay, so for 100, what is the mapping? 0 4. That means 100 is present at these two indices, and if we are at this index we can visit this, and if we are at this index we can visit this. So this mapping has to be present, right? That will tell that okay, other than going to left and right, we can take these jumps also, right? This jump and this jump, that would be told by our map. That's the reason why we created the map, right? Okay, if that number is present, then iterate on the list. Which list? This list. In this. Okay, if that index was not visited, add that index to the queue and mark that index as true. Fine. So all the 3 tasks are done. Now comes this part. This part is really important. Now let's see what it means. Let's say we have an array 7 7 3 5 7 7 and 1. The indices are 0 1 2 3 4 5 and 6. We started at 0, right? We added the left, that is minus 1. We didn't add it. We add the right, and we added 4 and 5 to our queue, right? These are the places where we can visit from this particular place, right? Okay, fine, we visited them. Now this place is done. Now when we finally come here, we will again do that same thing. We will check left, right, and we will check right, and we will check all the other places where the value is same, so that we can visit, that is 4 and 5. And eventually we will be adding this 2 as well as this 4 and 5 into our queue, right? But the thing is, we already added this 4 and 5 in our queue. there is no sense in adding them again, right? Otherwise when we come here we will again add 0 and 1, we will again add 5. So this way, in this way our queue size is going to increase again and again and again for nothing, right? So for that reason, when we have this mapping 0 1 4 and 5, okay, after we add all these visitable places into our queue, okay, we will simply delete this mapping. That yes, our queue knows that these positions need to be visited, my job is done, okay, and as soon as its job is done it will be fired. Okay, now your work is done, get out. Okay, otherwise there is no sense in adding the same visitable places again and again and again, right? So that's the reason why we are deleting that particular mapping. And at the end, after this while loop is done, we increase the number of steps. Why? We were at 0, this while loop added these two indices, right? That is, it discovered all the places, all the indices we can visit by taking one step, right? We visited 1 and we visited 4, which means finally one step has been taken and all places has been discovered. So we finally increase the number of steps. Okay, there might be a confusion that why not incrementing steps before. We can't increment the steps here because let's say we are at index 0. Okay, we will add that to our queue, right? Then we will pull it out. Okay, now in case our array size is 1, array size is only 1, let's say this. Okay, then this 0 is only going to be the last position, right? So before even checking if it's the last position, if we directly increase our steps is going to increase from 0 to 1, right? But we haven't taken any step, we just put it in the queue and just check that if it's the last position or not. We haven't taken any step, right? We are taking the step later after discovering all these visitable places, isn't it? So that's why after adding all the visitable places we finally increase our step. And in case if we didn't reach our last index, then we return -1. Okay, so let's run it, let's submit, accept it. Now what is the time complexity? The time complexity is a big O of n. Why big O of n? We traverse this whole array and we carried out a BFS, which is a big O of n. If you observe, we are going to visit all the indices only once. Why not more than once? Because our visited array and this removal of our map is preventing us from visiting any node more than once. Okay, I hope it's clear. So big O of n, right? And our space complexity is big O of n. Why? Because we have our queue will store at max n elements, n indices into it, and this visited array is taking a solid n space, right? It's a n sized array, so our space complexity is also big O of n. Okay, so I hope it's clear. If you have any kind of doubt, you can ask me in the comment section. And other than that, if you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next video. Bye bye.